Hello and welcome back to Machine Learning. I'm Jivita Christie, and in this video, we are going to talk about biological neurons, artificial neurons, and activation functions. So from this video onwards, we are going to be starting neural networks and topics like deep learning and RNNs and convolutional networks because now we are going to start to study a bit more advanced type of machine learning, the kind that it cannot be classified as, just as supervised or unsupervised. So, which is why we have to first understand neurons, because this kind of machine learning sort of captures the way the human brain works with, all the neurons in the brain and stuff like that. So, based on all the neurons that are present in the human brain, we're going to see how a machine can be developed to, and so that it can also learn in the same way in which human beings learn with the neural network that is present in the brain, which is why we are first studying biological neurons, and then we are studying artificial neurons, and activation functions are functions which allow the neural network to work. So we're going to see all these things in this video, and then proceed towards learning about neural networks and how to implement them. So let's first begin with what biological neurons are, because being a computer engineering or computer science subject, the people studying this are going to be studying in the context of IT engineering, computer engineering, and so we do not have a biological background, which is why it is important for us to understand first, how biologically the neuron works, so that then we can understand better how artificially it works. So the human nervous system has two main parts, and the first part is the central nervous system, which consists of your brain and the spinal cord. So the spinal cord is nothing but the backbone that you have on your back, and it is present in all the vertebrate people. So you have all vertebrate animals have a backbone, and so that is known as the spinal cord. So we have the brain and the spinal cord, and we also have the peripheral nervous system, which consists of nerves and ganglia outside the brain and the spinal cord. So there is also the peripheral nervous system, which contains nerves and ganglia, and this whole thing is connected to the brain. So whenever there is anything happening in your body, if there is pain in your hand, you feel the pain because you have nerves in your hand which are getting affected, and that signal is being sent to your brain, which is why you feel the pain, because your brain tells you it is painful. So that's how the body functions. That's how we have a nervous system. And the main part of that is the brain. Let's first talk about CNS, which is very important, the central nervous system. It integrates all information in the form of signals from the different parts of the body. So its task is to gather signals from different parts of the body and combine those signals to create information. And the peripheral nervous system, on the other hand, connects the CNS with the limbs and organs. So we all have organs, and we have limbs. Limbs are just, all the organs which are at joints. So you have a joint between your upper arm and your lower arm. You have an elbow. So those are limbs, basically, which are, connected with joints. So whatever organs you have, organs would be, heart is an organ, stomach is an organ, but hands and legs and all, they are limbs. So you have all these things which are connected to the brain uh, through the nervous system. Okay, so that's the peripheral nervous system. And neurons are the basic structural units of the CNS. So just like you might have studied in biology when you were in school, that cell is the basic unit uh, of any organism. Right now, we're talking about the CNS, which is the central nervous system. And for the central nervous system, the neurons form the basic structural units. And a neuron is something that is able to receive, process, and transmit information in the form of chemical and electrical signals. So, yes, there is a lot of chemistry and electricity going on within our body itself in the central nervous system, because that's where the neuron comes in. So, the neuron is something that can receive all these chemical and electrical signals. It can also process these signals, and it can also use these signals to transmit this information. Now let's talk about the neuron in detail. So the neuron has three main parts to carry out the primary functionality of receiving and transmitting information. And those three parts, the first part is the dendrites, which are used to receive signals from neighboring neurons, because you don't just have one neuron in your brain, you have so many neurons in your brain, which are all connected with a neural network. And each neuron has these three parts because information has to travel from one neuron to another neuron. So the first part you have is dendrites. Dendrites are simply used to receive signals um, from the neighboring neurons. Okay, and you have the soma. The soma is the main body of the neuron, which accumulates the signals coming from the different dendrites. It fires when a sufficient amount of signal is accumulated. Okay, so the soma is basically gathering the signals from the neighboring neurons, which means the dendrites are gathering the signals. The soma actually puts these signals, or sort of aggregates and combines these signals together. And when it has enough number of signals, it is going to fire. And then we have axon, which is the last part of the neuron, which receives signal from the soma. And once the neuron fires and passes it on to the neighboring neurons through the axon terminals. Okay, so axon terminals means to the adjacent dendrite of the neighboring neurons. So basically, it's a system of passing information from one neuron to another neuron. So the way that works is you have the dendrites that receive the signals. You have the soma that will gather all the signals together. They will accumulate or combine signals. And when there's enough number of signals received, then everything proceeds to the axon. And axon is the last part which you will actually fire. So that means you've gathered enough information, gathered enough signals. Now you have to fire those signals just like you'd fire a gun, and the bullet goes somewhere. In this case, the bullet would go to the next neuron. So information is passed from one neuron to another neuron using these three components. There is a very small gap between the axon terminal of one neuron and the adjacent dendrite of the neighboring neuron. Okay, so neurons are very closely packed with each other, and each neuron, the axon of each neuron, is very close to the dendrite of the neighboring neuron, which is why it is so easy to pass information from the axon to the dendrite. And this small gap that is there between the axon and the axon of one neuron and dendrite of another neuron is known as the synapse. And the signals that are transmitted through the synapse may be excitatory or inhibitory. Okay, so the signals could either excite the neuron, which means make it work more, or they could inhibit the neuron, which means they would make the neuron work less. So those are the two terms we have here. So here is a structure, a diagram of a neuron. So you can see this is the neuron, and this is basically some other neuron from where the information is coming. And here as well, you can see there's another neuron. All these parts are belonging to another neuron. So these portions right here, these elongated portions, they are dendrites. This middle one, which is a circle, is the soma. Okay, and what you see here, this is the axon. So this part is the axon, and this is the axon terminal. Okay, so from here you can see there is another neuron coming in, the dendrite of another neuron. So that's where the information is going to go. Now since we know a little bit about the biological neuron, let's now explore the artificial neuron. So the biological neural network has been modeled in the form of ANN, with artificial neurons simulating the function of biological neurons. So that's basically what's happening here in a computer. You are trying to create a program that's going to mimic the way human beings do their transmission of information. And that's why we have an artificial neuron. Each neuron, in this case, we're talking about the artificial neuron now. So every artificial neuron also has three major components, just like uh, a biological neuron has dendrites and axons and soma. So what does that have? The first component is a set of eye synapses having weight wi. Okay, so each you know what are synapses? Synapses are the gaps between the axons and the dendrites. Axon of one neuron and dendrite of another neuron. So in this case, basically, an artificial neuron has eye synapses having weight wi. So weight, this is just a function that is attached. And there's also signal xi, which would form the input to the eye synapse, having weight wi. And the value of the value of weight wi could be either positive or negative. If it's positive, it would have an excitatory effect. If it's negative, it would have an inhibitory effect on the output of the summation junction, which is y sum. So there is a junction. This is basically soma that's going to gather all the signals and pass them on somewhere else, which is the summation junction, which is depicted here as y sum. So the second part of your neuron is the summation junction, where the input signals, which are, the weighted input signals, are all gathered together along with the respective synaptic weight. And it's just going to combine everything. So this is just like the soma of the biological neuron. And because it's a linear combiner or adder, you can represent it in this manner. So it's just simply the addition of all the weighted xi values, the signals that you're receiving, multiplication with the weights, and then adding them. Um, and you could also have it in this way. So here B stands for bias, and you will later on learn what that means. Now let's talk about the third component, which is a threshold activation function, or sometimes simply called the activation function, also called the squashing function, which would result in an output signal only when an input signal exceeding a specific threshold value comes in as an input. So this is where, um, excitatory and inhibitory comes into picture. So if you see that there will always be a threshold that is set up. So threshold is something that is the limit. So there is a limit set up, and if the signal that's coming in it goes beyond that limit, then the output signal is generated by that particular neuron. And so in this case as well, we have a limit set up, and if the output signal if the input signal has crossed that limit, and that limit is set up by the threshold activation function. So if that limit is crossed, then the output is generated. And it is similar in behavior to the biological neuron, which transmits the signal only when the total input signal meets the firing threshold. So then it is excitatory if it's transmitting, otherwise it is inhibitory. So here you can see what an artificial neuron looks like. So you don't see a lot of curves and all because this is an artificial neuron, not the real one. So this is what it looks like. What you can see here, this is the soma basically that is gathering all the input signals. Okay, so this is nothing but all your dendrites that are getting all the input signals. These are the synaptic weights. These are the input signals x1, x2, and up to xn. And whatever is gathered here is converted into a sum. So everything is added, and an activation function is applied. So it's going to check if this sum meets a threshold value, a limit or not. If it's going beyond the limit, then an output signal is generated. So that's how this artificial neuron works. And the output of the activation function, which is y out, can be expressed as follows, which it's equal to just the function of y sum, which is the activation function. So the first kind of activation function is the identity function. And basically, this is the function used for the input layer, and it's linear, and it has this kind of a sorry, it is used for the output layer, but it is used as an activation function for the input layer. And it is a linear function having this kind of a form. So here y out is equal to fx, which is equal to x for all x, which means basically the output remains the same as the input. So in this kind of a function, there is no, it's just like not having an identity function, because whatever is the input is the same as the output. The next kind of function is the threshold or step function. So this is a step function, which you can see here. It starts from here and goes here and here. So there is a 0 and there's 1. And this is the threshold function, which is going in this manner. So there is a theta value involved. Let's take a look at what that means. So the step or threshold function is a commonly used activation function, as we just saw in the figure. The step function gives us a 1 as output if the input is either 0 or positive, right? So let's take a look at the figure again. So the threshold function, the step function is going to give us 1 as the output if the input is either 0 or 1, okay? So it doesn't matter what the input is, either 0 or 1, it's going to give us 1 as an output. And if the input is negative, then the step function gives us 0 as an output. So if input is either 0 or positive, you get a 1. If input is negative, you get a 0. And mathematically, you can express it like this. Y out is equal to f of y sum, which is equal to 1 if x is greater than or equal to 0, and 0 if x is less than 0, which means if x is negative. So this is your threshold or step function. The other kind of function we have is known as the RELU, or the rectified linear unit function. It is the most popularly used activation function in areas such as convolutional neural networks and deep learning, which are, even advanced kinds of neural networks, which we will be studying later. And this is the function that is preferred over there. So this rectified linear unit is like this. It is equal to x if x is greater than equal to 0, which means x is positive, and it's equal to 0 if x is negative. So like I said, it is 0 when x is less than 0, but it is equal to x when x is above or equal to 0. And this is what the function looks like. So you can see the function is equal to exactly x if x is anything other than if x is anything other than less than 0. So if it is less than 0, you're just going to get 0. But if it is greater than 0, if x is greater than 0, then or 0, then you're going to get exactly whatever the value of x is. So this y is actually your function, and the x-axis is the value of x. And this function is differentiable, except at a single point, which is x equal to 0. Other than that, everywhere else it is differentiable. So in that sense, the derivative of an ReLU is actually a subderivative because it is not differentiable at 0, but it's differentiable everywhere else. Let's now talk about the next kind of a function, which is the sigmoid function. It is by far the most commonly used activation function in neural networks. So just like just like ReLU is used more in deep learning and convolutional networks, the sigmoid function is very popular in neural networks. And the need for the sigmoid function stems from the fact that many learning algorithms require the activation function to be differentiable and hence continuous. Okay, so the function that we just saw was not completely differentiable, but in a neural network and many learning algorithms, we would want a function to be differentiable as well as to be continuous. And the step function that we just saw is definitely not suitable in those situations because it's definitely not continuous. Because it either gives you a 0 or it gives you a 1, but nothing in between. So it's not continuous, it's discrete. And so it's not suitable for such algorithms that require a function that is continuous. So there are two types of sigmoid functions. You have binary sigmoid function and the bipolar sigmoid function. Let's talk about the binary sigmoid function. It looks something like this. So you can see there's a curve going on. It's not a step like in the step function because this is a curve between 0 and 1. And because it's 0 and 1, it is binary. And the bipolar function includes -1 as well. So it's not just 0, but -1 also. So it's not just 0 and 1, but -1 also. So it is bipolar. Let's first talk about the binary sigmoid function. It is of this form. Fx is equal to 1 upon 1 plus exponent raised to minus kx. And here k is the steepness or slope parameter of the sigmoid function. So we just saw that the sigmoid function is actually a curve. So the curve has some slope, and that slope is the value of k. And if you vary the value of k, then sigmoid functions with different slopes can be obtained. And the binary sigmoid function has a range between 0 and 1. And the slope at the origin, which means at 0, is going to be k divided by 4. And as the value of k becomes very large, the sigmoid function becomes a threshold function, just like so that means if k becomes very large, if you make the slope very large, then it's no longer going to be a curve. It'll just become a straight line, and it'll just look like the step or threshold function that we saw, which was discrete and not continuous. Let's now talk about the bipolar sigmoid function. It is of this form, fx equal to 1 minus exponent raised to minus kx upon 1 plus exponent raised to minus kx. And the range of values of sigmoid functions can once again be varied for depending on the application that you have. So you can change the range of these values. But the preferred value or the most commonly used value is -1 and +1. So that is the most commonly used value for a bipolar sigmoid function, but you could have any values you want. But this is just the one that is preferred or most widely used. The last kind of function is the hyperbolic tangent function, which is another continuous activation function. And it's also bipolar in nature, which means it's not just about zeros and ones. You could adapt it for any kind of values. And it is widely adopted for a special type of neural network, which is known as a backpropagation neural network. And we will be studying this in detail later on. This right here is the form of the hyperbolic tangent function. it looks like this: e raised to x minus e raised to minus x upon e raised to x plus e raised to minus x. So that's what the function looks like. And remember, it's used for backpropagation, which we will be studying later on. So that's it for this video. I'll see you in the next one. Thank you for watching.